And our next speaker, Professor Alex Martsinkovsky from Northeastern University. And his talk is the Auslander-Gruson-Jensen duality and linear control system. I think the microphone is muted.
Sorry about that. Yes. All right. Thank you very much for inviting me to speak at this conference during these terrible times when Ukraine is under constant barbaric attack by hordes of war criminals. Like many people around the world, I'm looking forward to the time when Ukraine is liberated and Ukrainians are allowed to return to their homes without fearing for their lives. And will definitely follow. Today, I want to talk about somewhat unexpected connections about functor categories and rather applied topic linear control systems. This is some of the references. I'll leave the references with organizers so we don't have to rush through them. So the structure of the talk is very simple. You don't have to understand anything. There are several basic concepts that will be covered today. And it's all about functors. And they will appear in our discourse via two theses. One of them is brand new. It's due to my recent PhD student, Alex Sorokin. It's about defects, a concept that I will define in a few moments. The other one is pretty old. It goes back to 1961 to the topologist Dmitry Fuchs. But it's virtually unknown. And I doubt that he ever formulated it as a thesis, but I think it deserves such a name. Now, both approaches lead to a duality between torsion and cotorsion, which I will also explain, and we'll end the lecture with a conjecture that offers an algebraic framework for the duality between controllability and observability of linear control systems. So let's start by recalling some basic facts about linear control systems. This is just a system, undetermined system of differential difference equations. This is not the only way to think about systems. There are many other ways, but today we will be thinking about differential equations. They come as systems equations with discrete time. Here you see x at the stage n+1, at moment n+1, depends on the previous stage at xn, and some input u. So what is u? Remember, this is an undetermined system, and u are just the three variables. They can be assigned any value. And in the second line, you see the output, what is called as the output of the system, which depends on the state of the system, xn, and on the input again. The continuous time variant looks very similar. So you have a differential equation, and then again, you have a certain description of the outputs. So T is the continuous time. Now, the higher order systems of linear differential equations or partial differential equations or differential equations with delays can all be rewritten in this form. Now, whenever we have a system, call it sigma, we have a dual system. So what happens here? Each of the matrices A, B, C, and D is being transposed. And after that, the block matrix A, B, C, D is being transposed. So BT and CT are interchanged. Now, this is something from the language of control theorists. So a system is said to be controllable if starting with any stage, you can reach any other stage in finite time. Another important concept is the observability of the system, and observability sort of refers to the backward direction. If you read all the outputs, then you can read all the entire state of the system completely. And the remarkable result here, which emerged in, I believe, in the 1960s, and originally due to Kalman and many other people later on, that the dual system is observable if and only if the original system is controllable, and vice versa. So let's try and sort of digitize the situation. Now, these systems of differential equations can be written in matrix form, very simple equations. Here, A is a matrix with m rows and then entries, and then columns. And the entries are taken from algebra of differential operators, which we denote by D here. X is just a column vector of unknowns. And in the language of modules, this is just a system of m linear equations in n unknowns. Now, if you have a left module D together with your system, you can produce an interesting abelian group, namely the solution set of that system in that module V. In general, like what we saw in linear algebra, this is no longer a module, it's just an abelian group. The reason for that is that the ring need not be commutative, but it's still a subgroup. And again, as you remember from linear algebra, if you start with solutions, say, in a field K, and there are n variables, then the subgroup will be the solution set will be a subspace of Kn. Well, here it's the solution space will be a subspace subgroup of Vn. So given a module, we produce the solutions. This is a functorial operation, and we arrive at a functor. So it goes from modules over D modules to abelian groups. Let's call it the solution space functor. Now, the remarkable result here, which is known as the Malgrange lemma, is that this functor is representable. And the module that represents it, here it is denoted by capital M, has a finite presentation by the transposed matrix. So the solution space functor, we call it S here, is just home from the Malgrange module into the variable, blank variable. Now, not every system can be controlled, and there's always a part of the system that cannot be controlled. Control theorists have a special name for that part of the system. It's called the autonomy of the system. So the autonomy of the system corresponds to a certain submodule of the Malgrange module. To describe it, I need to recall the notion of the Bass torsion. I don't think it's an accepted terminology. It's not really mentioned this way, but I think we should call it the Bass torsion because it was Bass who first introduced this concept in his approach to torsion. So this is just the kernel of the canonical evaluation map from the module to its bidual. So it's a very simple definition. And the remarkable result here, which goes back to Pomeré first, and then in a slightly more general situation to Michel Flies, that the autonomy of the system corresponds to the torsion, Bass torsion submodule of the Malgrange module M. So the Bass torsion is clearly a subfunctor of the identity functor. So just to cut on the notation, with the submodule, I'm sorry, the subfunctor T, one is the identity functor, and the quotient functor will be denoted by T inverse. So if T is the autonomy, the uncontrollable part, then we can call T inverse of M the controllable part. Although this is not exactly the part of the system because it's a quotient of the module. And the question that arises now, whether there is an algebraic context for the duality between controllability and observability that was observed in control systems. So I want to approach this problem from two different directions. We will see that they provide the same answer. The first one is related to the notion of defect. And here I need to recall the definition of a finitely presented covariant functor F. So any such functor sits inside a four-term exact sequence. So the first three functors are the home functors, they're representable functors. The last map by the Uneda lemma is induced by the map on the argument. So that's just the map from capital A to capital B. And the defect of this functor, finally presented functor, has a very simple definition. That's just the kernel of that map, small f, from capital A to capital B. It has many remarkable properties, but maybe the first one to mention should be the fact that the zeroth right-derived functor of the functor F is representable, and it's represented exactly by the defect of the functor. So if you have no interest in learning anything about functors, the only thing you should remember from this lecture maybe is that the zeroth derived functor of an arbitrary finally presented functor is represented by the defect. And being a kernel, of course, it's a module. Now let's dive into deeper properties of the defect. So this yen sign denotes the contravariant unity embedding. It takes a module and produces the corresponding home functor, covariant home functor. The remarkable fact here is known as the op-Uneda lemma, which says that the defect and the Uneda embedding form a right adjoint pair. Remember, these are contravariant functors, so we don't have left and right. They're either both left or both right adjoints, and here they are both right adjoints. So we say that this is a right adjoint pair. And you might have seen closely related name co-Uneda lemma. That's how it is usually called, but my student tells me that it should be called op-Uneda lemma because we're reversing errors. Well, actually, the picture is much richer. The defect W, it's the horizontal arrow in the middle that goes from finally presented functors to modules, is not only part of a right adjoint pair, but it is also part of a left adjoint pair. That's the arc on the top. That's the other part of the left adjoint pair. That's the zeroth left-derived functor of the net embedding. Whatever it is, the conclusion here is that the defect W is a contravariant by adjoint and is therefore is an exact functor. Now, for contravariant functors, the situation is very similar. Now we have a sequence of contravariant horns, and the definition of the defect here, which is denoted by V of F, is it's the co-kernel of the map that induces the presentation of the functor F. That's also denoted here by small f. And you can see it immediately from this definition. This is just evaluation of the functor F on the regular module lambda. And already from this, it follows that this defect is an exact covariant functor. And the properties of this functor are parallel to those of the defect W. And exactly as it was the case for covariant functor, the defect here represents the zeroth right-derived functor of F. The defect is ubiquitous. When I started looking at the defect closely a couple of years ago, I was astonished by the ubiquity of this concept. It's everywhere. We don't have enough time today to go over the examples, so I will just go very quickly over very few examples. So the first trivial example is that the defect of a representable functor is the represented module. It goes follows straight from the definition. Well, when is the defect zero? Defect is the kernel of F. And the kernel of F being zero means that this A, B, and C fit in a short exact sequence. Thus, you can say that the kernel of a functor is zero. I'm sorry, the defect of a functor is zero if and only if the functor comes from a short exact sequence. For example, if you take the Syzygy sequence from module A, then you immediately deduce that the defect of X1, covariant X1, is zero. Here's another useful criterion. The defect of a functor vanishes if and only if the functor vanishes in injective modules. And that gives us another proof that the defect of the covariant X is zero. And notice that this proof does not require the existence of projectives. For exactly for the same reason, the defect of any right satellite is zero. And if S1 of F is finally presented, but we are moving in the direction of defining the defect for any functor, not just for finally presented functor. So we will see that this restriction can be removed. Another example, and it's very simple to compute by hand, that if the functor is non-zero and has projective dimension less than or equal to 1, that means the module C in that presentation that I showed you before is zero, then the defect is non-zero. All right. Such functors appear in model theory of modules. We already mentioned systems of linear equation and modules and all such, or projections of such systems, and all such functors have projective dimension less than or equal to 1, and therefore the functor is non-zero. Such a functor cannot be given by a linear system or projection or a finite system of linear equations. The projected dimension less than or equal to 1 means it's either zero, and we already saw an example when we discussed the Lagrange module. So that's exactly the solution set of a linear system. That's the functor that arises this way. And when you take projections in the language of logic, that amounts introducing existential quantifiers for this system. And it's a theorem of Kevin Berg that in this case, the projective dimension of such a functor is exactly 1. So one consequence is that x1, whose defect is 0, cannot be given as a solution set or a projection of such a solution set of a finite system of linear equations. Here's another familiar example. This is universal coefficients for cohomology. You're looking at it. Look at the last map. So the functor is in the middle. And that map, we all know, is an isomorphism on injectives, forming into injectives preserved homology. And also notice that the range that is formed from HN, C into blank, is left exact. But these two properties characterize the zeros derived functors. So the last entry in the sequence is nothing but the 0th right derived functor of the middle functor. And this functor is representable. You see, it's represented by the nth homology. And therefore, without any work, we computed the defect of the nth homology functor. Now here, C is not any functor. It is supposed to have, it's a complex of projectives with projective boundaries. The duality for finitely presented projectives very quickly leads to the conclusion that the defect of the tensor product, whenever the fixed argument is finally presented, is a dual. So combining with our previous observations, we now see that if the dual of the module is 0, then if the module is A, then A tensor that module vanishes on injectives. This leads to a very interesting consequence. If you use Nakayama's lemma, then you can easily prove that, say, projective, if say commutative ring has depth at least 1, then all injectives are infinitely generated. But that's just a sideline remark. So how much time do I have left?
I think 15 minutes.
10 minutes.
15.
Okay. Oh, 15.
Yeah.
Thank you. So now let us define the defect. That's a recent definition of an arbitrary additive functor. So I am recalling here the op-Yoneda lemma. This is the fact that the Yoneda and the defect are part of a right adjoint pair. And I'm going to evaluate this isomorphism on the regular module A. So we replace A with lambda, and we immediately see that the defect is the class, actually a set of natural transformations from F to the Yoneda embedding of the regular module. And this isomorphism, look at the right-hand side. It is defined for any functor F, whether it is finally presented or not. And we're going to take this as a definition of the defect of an arbitrary functor. And by the way, this yen of lambda, this is just home from lambda into lambda, is called the forgetful functor. That's probably the most interesting functor of all. Well, now that we have forced a new definition, we can ask whether the Yoneda, op-Yoneda lemma remains true, and the answer is yes. So still the new defect and the Yoneda embedding are still part of a right adjoint pair, and you do it by using a theorem of Wards. Very quickly, a few more examples. What is the defect of the tensor product? Well, you're looking at the natural transformation from the tensor product into the forgetful functor. But the forgetful functor can also be affected not just by home from lambda, but also tensoring with lambda on the other side, for example. And but the natural transformation from A tensor blank to lambda tensor blank are the same. It's not difficult to show as the maps on the arguments. That is the maps from A into lambda. So that's A star. And we have just proved that the defect of the tensor product is the dual of the argument, regardless whether A is finally presented or not. Well, another quick example, if you take an ideal in a commutative ring R, and you look at the I torsion functor, it's defined as the union of all in a module A, it's the union of all elements annihilated by various powers of the ideal. You write this as the direct limit of these Holmes. And in general, this functor is not finally presented. Nevertheless, we can compute the defect. Remember, being part of a right adjoint pair, defect takes core limits and turns them into limits. So you see the calculation. So we have a limit in the first place, and then the defect of a representable functor, which we know is just the representing object. And when you pass to the limit, you get the I-adic completion. So the I-adic completion is the defect of the I torsion functor. And now we come to Alex Sorokin's thesis. It's a little, the title is a bit humorous because the term thesis here, my original intention was to call meta theorem, but then I consulted with logicians and they told me not to use this term because meta theorem is a theorem. Now, the thesis is a more appropriate term here. It's a principle. Alex defended his thesis less than a year ago. He generalized this, what I just explained about functors, to a very general setting. I don't want to go over all these technical details, but let's go to his thesis. Everyone is familiar with MacLane's thesis, which says that all concepts are Kahn extensions. What Alex showed that Kahn extensions and Kahn lifts are defects. And therefore, we have Sorokin's thesis. All concepts are defects. So Alex is very shy. He doesn't want to call this Sorokin's thesis, but I think he deserved this thesis to be named after him. And given a choice between MacLane's thesis and Sorokin's thesis, I choose Sorokin's thesis, not because he was my graduate student, but because defects are very concrete and much more computable. Now, let's see. I am going, if everything is a defect, how about the autonomy? Well, let's take a look. Before making a statement, I want to recall the definition of Hom modular projectives. And this is just the usual Hom, except that you mod out by the subgroup of all maps that factor through projectives. And here we come to a theorem which says that the defect of A modular A comma blank modular projectives is exactly the best torsion of the module A. All right, so if you can apply it to the Lagrange module, and remember, the torsion of the Lagrange module is precisely what is it? That's the autonomy of the system. So we have expressed the autonomy of the system as a defect, as was promised. And now we're after duality. So how do we dualize this concept? Well, let's take a look. So we started with M comma blank. So the proper dual concept would be the contravariant Hom, blank comma M. Before we took M comma blank modular projectives, now we take blank comma M modular injectives. We dealt originally with a covariant functor. We had the defect W. Now we have a contravariant defect. So we have to take V of that. And remember what V is. That's just a valuation on the regular module. So this is just Hom from lambda into M modular injectives. And the quotient modulo M we'll call this the cotorsion of M. It's a very simple definition. Of course, it's a quotient of Hom from lambda into M, which is M. So this is just a quotient module of M. But we sort of answer the question. We have a sort of duality between autonomy and which is torsion, and the cotorsion. The problem with this is that this duality seems to be a duality of concepts. It doesn't seem to be affected by a functorial duality. Where's the functor? How do we compute this duality? So for this, we need an alternative approach, and that's where stabilization of additive functors come into play. I want to recall that the canonical natural transformation between functors and their zeros derived functors. And if you go from the functor to its zeros right derived functor, the kernel is called the injective stabilization of the functor. That's the largest subfunctor of F, vanishing on injectives. It's an additive functor because it's a subfunctor of an additive functor. And there's a simple way of computing it. And when I say simple, it means theoretically simple. If you want to compute the injective stabilization of F on a module B, embed B into an injective container, apply the functor, and compute the kernel on that map. So this way you get this defining sequence for each component of the injective stabilization. Now, you can play this game with a tensor product, and with the tensor product, I want to modify the notation. Rather than using the overby, we'll use the harpoon. The harpoon has that half arrow, and it points at the variable which is to be embedded into an injective. Like any bifunctor, well, you know from homological algebra that you have an active variable and you have an inert variable. With classical functors like X or Tor, you know these functors are balanced. So you can choose a resolution on one side, or you can choose a resolution on the other side. Well, that doesn't happen with injective stabilization, especially with injective stabilization of the tensor product. So for this, we need an accounting tool that reminds us what is being embedded into an injective. Now, the results are quite different, and the injective harpoon always points to the active variable. And projective stabilization is defined similarly. Instead of taking a subfunctor of F, you take a quotient functor of F. And here comes one crazy observation due to this contravariance. If you take the projective stabilization of the contravariant functor, you end up with Hom modular injectives. But that's how things are. Well, here's the picture to summarize what we have seen so far. The letter P stands for projection. The letter I, all in circles, stands for injections. And they're always next to the functor F. So injective and projective stabilization actually don't have anything to do with injective and projective resolutions, but they have to do with projections or injections. Okay, so now we can define torsion in a different way. We start with a regular module embedded into an injective. Am I right? I still have 5 minutes.
It's about true.
Yeah, okay. So let me accelerate a little. So let's embed the regular module into an injective. Okay, and let's tensor it with a module A. So the kernel of this map will be called the torsion. You see the German S of A. That's our definition of torsion. Now, we'll quickly look at the properties of torsion. So the torsion we have just defined is always a subfunctor of the best torsion, but on finally presented modules, it coincides with the best torsion. And by the way, the Lagrange lemma and all applications in control theory, you're dealing with finite systems, so you're automatically dealing with finally presented modules. Another useful thing is that the new torsion preserves filtered colimits, and it's the largest subfunctor of the best torsion that preserves filtered colimits. So we remember that the best torsion was the autonomy, and that's the same as our torsion S. And so we have defined the torsion that we defined via the defect W coincides with the torsion that we defined via the injective stabilization of the tensor product. What about cotorsion? Well, we use a dual approach. We started with, for torsion, we started with the injective stabilization of the tensor product. For cotorsion, we'll do the projective stabilization of the contravariant Hom functor, but we just did it a moment ago. Here's the definition. So this is just Hom modular injectives from lambda into C. And that is exactly what we obtained using the defect approach for the cotorsion. So the cotorsion defined via the defect V coincides with the cotorsion, should be cotorsion here, sorry, via the projective stabilization of contravariant Hom functor. Okay, so here's where Fuchs's thesis comes into play. He says, for a precise definition of duality, replace a duality of concepts by a duality of functors. So we just need a duality between functors, and it is fetched by the Auslander-Gruson-Jensen functor. What is it? Well, there's a certain functor T. What is it? It interchanges tensor products and Hom functors, and it is also exact. And these properties define this functor uniquely. And we'll take this as our proposed duality here. It takes the projective stabilization of Hom into the injective stabilization of the tensor product for any module B. If we specialize to the regular module, then we see that the duality on applied to cotorsion gives us a torsion. And one last step. This is duality of functors, but if you face an engineer needs to work with concrete modules. So how do we produce a duality on modules? This is possible. This is, well, look at the first display. So here's the situation. The ring is now assumed to be an algebra over a commutative ring R. It's not a restriction because this R could actually be the integers. We choose an injective R module J. Dj will denote the duality, or rather Hom into J. And the theorem says that when you apply this Hom into J to the injective stabilization of the tensor product, you get the projective stabilization of the Hom functor. And below you see the rather compact version of this statement when you specialize B to the regular module. Now, if this is true for S and Q, remember S was the autonomy, so S inverse will be the controllable part. Q will then be the non-observable part, therefore Q should be the observable part. So this is a duality which can be evaluated on modules. In particular, if you take the character module, when you take integers for in place of your ring R, and you take Q mod Z as the injective module, you see that the character of the torsion-free part is the cotorsion of the character module. And so we finish with the conjecture that observability must be related to cotorsion. This is the conjecture. Thank you.